Hello, guys. Welcome back. So today we're gonna continue with this topic for shortest path, single source shortest path problems. Okay, so this is where we stopped on Tuesday. We looked at there are several variants of the shortest path problem, and we're looking at this particular type of single source, which means we only consider one source vertex and vertex, and we want to compute the shortest path from that source vertex to all the other each of the other vertex in the graph. Okay, so we haven't yet finished the preparation part, so we're gonna look at what other properties we need to know about the shortest path problem, and then we will start talking about the algorithms to find the single source shortest path. Right. So I will do my best to cover all the both kind of single source shortest path algorithm today, so that you can start working on the last assignments. So next week we can start a new the final chapter of this course. All right. So yeah, let's look at the optimal substructure. Well, I guess you may be familiar with this term, right? Optimal substructure, which is the term that we use in the dynamic programming problems, which basically says that the solution to the original problem can be decomposed into the solutions of the sub-problems. And these substructure, optimal substructure, also exists in the shortest path problem. Okay, so to put it simply, we can say that a shortest path between any two vertices contain other shortest paths within it, right? So in another way, we can say that if you take any segment out from a shortest path, then it must be also a shortest path for that two vertices we selected. Okay, so here's a lemma that basically formally define this property. Say these series of vertices from V0 to Vk. So this is a typical way that we use to represent a shortest path, right, from the source, which is V0, to the destination, which is Vk. Okay, so if we take any vertices within, like any subpath from this path, say if we select any I and j that's between 0 and k, right? And these subpaths from Vi to Vj must also be the shortest path from Vi to Vj. Okay. So I think this is a very straightforward property, because if you can find any segment that could be shorter, right, which is not exactly the shortest path, then the whole sequence, the whole path, then also breaks the shortest path problem. Okay, so that is I think it's a very straightforward property, and which will also be useful in some of the following other theorems. Okay, and before that, let's look into the issue of negative weights edges. Okay, so this is a first time that we deal with this special kind of weights, right? Because in a spinning minimal span tree problems, we basically maximum spanning tree problem, we basically don't have a negative weight, right? We basically have all positive numbers. Then in this case, when we try to find the shortest path, then we will introduce this problem, because in some cases, the negative weights for the edges may also have reasonable meanings. For example, if we use the negative number to denote the directions of the transfer from account to the other, right? So sometimes the number can be negative numbers. So the existence of negative weight edges actually makes the problem more complex, right? Because in general, we want a graph to contain no negative weight cycles, okay? Right. So that is our general requirement, right? If we want to compute the single source shortest path from the source vertex S, then we want there should be no negative weight cycles. And in the next slide, we're gonna see why there will be a problem if we have such negative weight cycles, okay? Because basically, if we have such a negative weight cycle, then the shortest path weight, this quantity for all the vertices will not be well defined. Okay. So a little bit review of this quantity. So this delta between two vertices U and V, it is the theoretical theoretical minimum point, theoretical minimum value for any path between U and V. Okay, so this quantity is the total weight of the shortest path between U and V, right? But the actual shortest path between U and V can be multiple. It can be not unique, right? But the minimal value is unique. So this number is indicated by delta, and we will see this delta a lot in the next couple of slides. Okay. Then, yeah, let's see why we should not have a negative weight cycles when we consider the single source shortest path problems. Okay, and typically we will say that if there is a shortest path, if there's a negative weight cycle in the graph, say from S to V, then we will say that the shortest path weight delta, we will simply set it to be infinite, because this is not a problem that can actually be computed. Okay, so for example, we have this graph, and there's some negative numbers associated with some of those edges. For instance, from A to B, and from D to C, right? And also from F to E is this number, right? So we have these negative weighted edges, okay? And you also see that there are some infinities, which means that the shortest path from the source to those vertices are actually not well defined. Okay, so let's see why this is the case. Because you see, the shortest path, because if we look at the right vertex of this first negative weight edge, right? If you look at this edge, and B is the vertex of our interest here, and there's actually only one path from S to B, right? Which has the total weight, which is 3 minus 4, which is -1, right? So that is why this shortest path value, the shortest path weight for the B is -1. That makes sense, right? Because there's only one path from S to B. But this is not the case for the path from S to C. Now let me clear all the colors. If you look at the path from S to C, right? Say, if you only look at the direct connection, the direct edge from S to C, then there's only one edge, which is 5, right? But the concept of path is different from a direct edge, because a path can consist of several edges. Like we can go from S to C, right? That is one path. Or we can also go S to C, right? And then C to D, right? And then D back to C, following these cycles, right? So this is also a path from S to C, because S is the source and the C is the destination, right? Regardless how many other passes we have, how many other edges we have between the S and C, right? But if we consider these, the path for these the weight for this pass, and we compare it with the third type, the third possible pass, which is actually you go one more cycle, right? You go from S to C to D to C, and then to D to C again. So it's just one more cycle between C and D, right? So that is also a pass, okay? Right, but the thing is that we will need to consider what is the total weights along the path. Okay, so in this case, the cycle, let's say one cycle from C to D and back to C, it actually has two edges, which is 6 plus -4. So the total weight of one cycle is actually a positive weight, right, which is 3. So in this case, the cycle is a positive weighted cycle. Okay, and this is actually good news for us, because we know that when the cycle is positive, then we will need to avoid going into that cycle for many times, right? Because the more cycles we go, the total weight will increase, right? So we know that the shortest path in this case is actually well defined, right? Which is to go to avoid going into the cycles, right? Say the shortest path for D is just from S to C and then to D, which gives the total weight 5 plus 6, right? Which is 11, right? And if you go into that cycle, like from D to C and then C to D back, that will make a +3 increase to the total weight, right? Which will make it 11 plus 3, which is 14. So which is not the minimal, which is not the shortest path. So in this case, this is actually where we accept is acceptable. This positive weight is acceptable because it doesn't violate, it doesn't bring any problem in our definition for the shortest path problem. Okay. But there will be actually a problem if we look at the third case, right? The third case, similarly, there's also infinitely many passes from S to E, right? So we can like go from S to E and then to F and then to E, back to E, right? We can go into that cycles for as many times as possible, right? But the difference is that in this case, if we look at the total weight of one cycle, which is 3 plus -6, which has a negative weight, okay? So that means the more cycles we go into, the less total weight we will have for the path. Then by the definition of the shortest path, right? Because we want to find a path that has the minimal total weight. Then in theory, we should go into that we should go into that negative weight cycle for infinite amount of times, right? So there's no, in this case, in the third case, the shortest path problem is actually not well defined. We will have to like put those negative infinities to those vertices, right? Because of the existence of these negative weight cycles. Okay, so now you see that the negative weight cycles actually is a problem that we need to deal with, and we need to basically want to avoid the existence of such a negative weight. All right, so let's look into the next slide. Actually, we take some we make some very strict requirements that a shortest path should not contain a negative weight cycle, right? This is obvious from the previous demonstration, right? If there's a negative cycle, then we actually, that shortest path can be even smaller, right? And we make it simple, a requirement that we should not also contain, it should not contain a positive weight either, right? So because removing the cycle from one pass will produce a path with the same source and destination with the same source and the destination vertices and the lower path weight, right? So we basically want to avoid this complexity in the graph, and by basically excluding by basically place some hard requirements that the graph should not contain any cycles, regardless of whether it's negative weight or positive weight. Okay. So we simply hold this no cycles assumption. All right. Okay, so next, let's see how we represent the shortest path. Okay, so this is some key technique we need to use, and actually it's something that we have already come across before, right? Because like we made an analogy to the breadth first search problem, right? Which is the first type of elementary graph searching algorithm, right? So actually, the shortest path in the graph can actually be represented by something similar to a BFS tree, right? Remember, in BFS tree, we use the pi property or the pi attributes for each vertex to remember for each vertex which is its parent vertex, right? We will need to use that parent attribute to trace back from each vertex to the source, right? So in the case of shortest path problem, we will need to use the same technique, right? We will basically set a v.pi attributes to remember the predecessor or the parents of the current vertex. Okay, so this vertex can be none if there's no predecessor for that vertex. Okay, for example, the source vertex, right? So we basically use the pi attributes to form a chain of predecessors for each vertex, and following that chain, we can basically start from a one vertex v and trace backward along a shortest path until to the source vertex, right? So it's just like tracing back from a leaf node in the tree to all the way up to the root node. Okay. So eventually a shortest path algorithm should return something that's similar to a BFS tree, which we can call a shortest path tree. Okay. The difference from a BFS tree is that now the distance contained in this shortest path tree actually is defined in terms of the edge weights, right? The distance is based on the weights along all the edges along the path, but not the number of edges, right? In BFS, we only consider distance as measured by the number of edges or number of edges away from the source, from the root to the leaf. Okay, so here's just some technique we will need to use. Okay, and then let's go inside the problem and look at the first basic piece of knowledge that we need to know about, which is the relaxation procedure. Okay, so it's really at the core of basically any kind of single source shortest path problem. Okay, so this relaxation is actually a very basic operation that is applied to actually two adjacent vertices. Okay, so it's a really elementary procedure, and it's the nature of all the other single source shortest path problem is just a repetitive execution of this relaxation procedure, right? We will need to first define this relaxation procedure as a basic operation, and then we will need to execute it for multiple times in order to get the single source shortest path. All right, let's enter this relaxation procedure. Okay. All right, so this procedure in this procedure, we basically maintain an attribute for each vertex, and that attribute we call it d. Okay, v dot d, and this d is for distance, right? We had similar attributes in BFS, right? If you remember, and this d, in this case, it is an upper bound on the weights of a shortest path from S to V. Okay, so it is not the final values. It is not the solution yet, right? But it is a some estimation or some candidate values that we need to maintain and update, right, in the graph. And at the beginning of the algorithm, these d values can just be initialized to some infinity, for example. And then later on, as we run the relaxation procedures, we will basically change that value and make it smaller and smaller until we reach the theoretical minimum point, which is the shortest path weight from S to V. Okay, so we can call it an estimate, and we basically initialize them to the value of infinity, right? So before we start computing the single source shortest path from the source vertex here, we need to basically initialize this d property to infinity. Okay, I think this makes sense, and it's quite similar to how we initialize it for the BFS, right? In BFS, I don't think we explicitly define this procedure, but it's actually the same initialization we need to do. Okay, except for the source vertex, right? Because source is where we start, so the distance will be initialized to 0 in this case. Okay, and what's in nature a relaxation procedure is doing is that it will take an edge as input. Okay, for example, that edge is from U to V, and the procedure will do such a test. It will examine whether we can improve the shortest path to the vertex V, right, can be improved by going through the vertex U, right? If so, right, so we will basically test whether the shortest path from S to V, right, whether this can be improved by first going to U and then U to V. If this way is better, then we will update the distance of V, and then also change this pi attribute. And do you know which vertex we should let this pi v dot pi points to? It should exactly be the predecessor or the parent's vertex U. Okay, so let's look at the pseudocode. Okay, right. So you see, so it's a very simple procedure. Okay, it will takes the two vertices as inputs, U and V, and also the weight function. W is the weight function. It contains the weight information for all edges, right? So with the relaxation written in by this relax procedure, it only contains one if statement. It will check whether the current value for the distance estimate to for the V vertex is greater than the d of U plus the weights of the edge from U to V. Okay, and if so, we will need to update the d of V by setting it to this smaller value, d plus the edge, right? And also the predecessor attribute should be set to U. Okay, so the meaning of it is that it compares two possible passes, right? The first pass is the original single source pass, which can estimate, which has this value. The other way is that we first go to U, right? The U.D records the path, the shortest path from S to U, and then we will go from U to V, right? Which means we need to add these weights from U to V. And if this is a better path, we will need to update the value for V, right? So this is a very straightforward procedure, right? And if it's not, it's the other case, right? If going to U makes the whole path farther away from the original one, then we simply don't need to do anything, okay? So this is a very basic operation, right? That is reasonable, right? From two vertices, we will simply check whether it goes through that edge will be a better option or not, right? So we will keep calling this relaxation in order to get the single source shortest path for all the vertices in the graph. All right. Okay. So basically, any kind of single source, a shortest path algorithm will call this. First, we'll call this initialization procedure, and then repeatedly call the relax on the relax procedure on all the edges. Okay, and the differences among all the algorithm is that some algorithms may call the relax with different order or with different amount of times, or with different number of times. Okay, and we can say that relaxation is the only means that's a shortest path problem, a shortest path estimates and the predecessor can be changed. Okay, so within the algorithm, the updates of these D and the pi attributes will only happen within this relax. Okay, so as for the difference in terms of how many times each edge is relaxed or the order of relaxing, we will need to compare these two algorithms. The first one is a Bellman-Ford algorithm. The second one is the Dijkstra algorithm. Okay. All right. I think we have a couple more slides before we introduce the Bellman-Ford algorithm. It's about the properties of the shortest path and the relaxation. Okay. So I think these properties are interesting to look at because not just because they are helpful in prove the correctness of the Bellman-Ford and Dijkstra algorithm, but also they reveal some of the interesting properties of graphs with weighted edges in general. So, for example, the first one, the triangle inequality. Okay, so it has a very strong mathematical background in it here, right? So it's like if you think of it as a triangle, right? Right. If you think of it, the path, it's actually a very good analogy to geometry, right? So like the path from S to V, it must be less than or equal to the path, the single source, the shortest path from S to U plus the weights. Okay. It's similar to the triangle inequality in elementary geometry, right? And the second property is upper bound property, right? Which says that our estimates for the for the shortest path, our estimation is always greater than the theoretical minimum points. Okay, and once this estimate has achieved the minimum points, it will never change. Okay, it's also called the convergence property, right? Which means that when we are relaxing all the edges repeatedly, once some vertex has reached the minimum points, then they will never increase again. Okay, so that's we are guaranteed to converge to some points. Not converted to a point that's the minimum, that's the the estimate for the shortest distance will reach the theoretical minimum points, minimum value. Okay, so some other properties, like say no path property. If there's no single source shortest path, we can simply set the d to infinity. Okay, and the path relaxation property, okay, it basically says that if we have a shortest path, right, from v0 to vk, it's actually, we can relax the edge of p in such order. Okay, if we relax all the edges in such an order, if we relax first v0 to v1 and then v1 to v2, and the last one be relaxed is vk minus 1 to vk, right? So the condition is that if we relax all the edges in such an order, then we will must have the d attributes of the last vertex will be the theoretical minimum point. Okay, so this is actually a very helpful property, right? So it basically states the condition of how to find a single a shortest path given the vertex given the source vertex and the destination vertex, right? And this is actually a quite strong property, because if you even if you intercept, you interpolate some other edges among these edges that forms these paths, the results will hold true. Okay, so this property will hold true regardless of what other relaxation steps will occur between these edges. Okay, as long as you make sure that you follow the order. As long as you make sure that you relax the first edge first and the second edge afterwards. Okay, so that is the path relaxation property. And the convergence property that we already mentioned in the previous slide, that once we have after relaxing some edge and the d attribute has reached the theoretical minimum points, then it will never change. It will never go up again afterwards. All right. So yeah, so after these properties of path relaxation has been gone through, let's start talking about the specific algorithms. Okay, so the first one is Bellman-Ford algorithm. Okay, and if we compare the two, the Bellman-Ford and the Dijkstra, I would say Bellman-Ford is implementation-wise, it's an easier implementation. Okay, but it has a more general application, right? It applies to more general problems. So because the assumption that we hold here is that we can tolerate the existence of negative or negative weights in this graph. Okay, we tolerate that there may be negative weights. Okay, so the existence of negative weights is somehow risky, because we know that if there is a negative weighted cycle, then the single source shortest path problem is not well defined. Right? We have a shortest path cycles in it. Then for some vertices, the problem is not well defined. So we have to consider that in Bellman-Ford, right? If we want to solve the more general cases where negative weights is a possibility, right? So we need to take this into consideration, okay? And what this algorithm does is that it takes the graph and the source and the weights as inputs, and it will return some Boolean value, okay? And that Boolean value is important because it indicates whether or not there is a negative weight cycle. Okay, so we have to examine whether there is such a negative weight cycle in the graph, right? That is reachable from the source. And if so, the Boolean value will return false. So that tells the caller of the procedure that our results is not correctly returned, right? We have to examine the inputs or change the inputs and so on. Okay, so yeah, so if there's such a cycle, the algorithm will indicate no solution. And if not, then the algorithm will produce the shortest path and their weights. Okay, so let's look at the procedure itself. Okay, so as we know, in the when we talk about relaxation, we said that any kind of single source shortest path problem, actually any kind of shortest path problem, is just a repeated execution of the relax procedure, right? So this is true for Bellman-Ford. So first, we will need to call the initialized single source procedure, right? Remember what we do in this procedure? We simply initialize the D, all the D's to infinity, right? And all the pi's to none. And except for the source, the D will be 0. Okay, so that's what we do in this procedure. And then from line 2 to 4, it's actually a nested for loop, right? So, but the code is clean. So we basically use the outer for loop, to make basically to make v-1 passes. Okay, so that's the first loop counter I will iterate from 1 to v-1. So that is almost the number of vertices. Okay, so that is the scope of the outer for loop, and it's fixed. And then the second, the inner for loop, it's also fixed, right? So the inner for loop goes through each edge in the graph. Okay, so it's actually a very dumb it's a really really stupid algorithm, right? It doesn't, consider the range of the for loops carefully. It just goes through. It's quite a brute force way, It's first use the I to go through v-1 times, right? And within each inner for loop, it will go through each edge once, right? So for the inner loop, it will go through each edge once and relax that edge. Okay, so each pass is just a one execution for the relaxation, for the relax on the edge. Okay, so you see there's a nested for loop. So you can basically estimate the number of relaxes being executed, right, within each inner for loop, right? So there will be basically the number of edge the number of execution would be this size of E, right? And outside it will be the size of E. So it's basically multiplication, right? You should use V times E to estimate the total number of times that the relax has been executed. Okay, so that is the main body between 2 to 4, between line 2 to 4. And next, the line 5 to 8, it's the to satisfy the requirements of the algorithm. We want to check whether there is a negative weighted cycle in a graph. Okay, so in this line 5 to 7 in the for loop, we will need to go through all the edges one more time. Okay, and for each edge, what we check is that we will see if the D of V will be greater than the U dot D plus the edge. Okay, so if U dot D, which means if you go from U, we go the U dot D means the shortest path estimation from S to U, right? So if we let S to U plus the edge from U to V, if we do that computation again, even if we have a smaller value than V dot D, which means that this cycle is kind of a negative, it's a negative weighted cycle, right? Because we go through that edge again, it will create a shorter path, right? So why not we simply go through that for infinite number of times? So that is the Q of, that is a sign of a negative weight cycle in it, right? So in this case, whenever we found such a anomaly, we will need to return false, okay? And otherwise, if after the whole for loop examination here, there's no such a case found, then we simply return true, which basically says that the algorithm runs correctly on the graph, which returns which contains no negative weight cycle. Okay, so let's look at an example. I think the algorithm is itself very clearly defined. It's like two for loops, right? We go through, we set a path for v minus 1 times, and then within each path there will be a loop, for loop that go through all the edges once, right? And then we relax each edge once within the for loop. Okay, so here's the illustrated illustration for a graph that has all the values initialized correctly, and our source is the S vertex, and the D's here are listed as numbers in the cycles, in the circles. Okay, so we need to assume that each path will relax the edges in such an order, right? We need to list all the edges here. So this order actually doesn't really matter. We just choose an arbitrary order in order to see how the algorithm runs. All right. So let's see. First, let's determine what's the number of vertices. It's 5 vertices, right? So the range of the for loop is from 1 to 4, right? 5 minus 1 is 4. So the outer for loop will have 4 passes, right? So that's our first pass here. And we need to go through all the edges in such an order. Okay, so we relax T, we will need to call relax on the edge from T to X. Okay, let's look at those values carefully, because the X dot D is negative, is infinity, and the D dot T is also infinity. So the comparison, basically the if condition is not satisfied, right? Because the two sides of comparison are both infinity, right? So there's no way to compare to infinity to get well, basically the greater than relationship is not satisfied, right? So we will do nothing in this relax, right? And for Ty, the edge from T to Y, also the two ends are infinity, so nothing will be done. Okay, so for these edges in the between, in the middle, because the two ends are all infinities, so nothing will be changed until we reach these points, until we reach the edge from S to T, which means the S has some, the D of S is 0 because it's initialized to 0, and the if condition in the relax actually is satisfied because the infinity is greater than 0 plus something, right? Plus the edge from S to T, which is 6. So the relax needs to make such a change, okay? It will change the D values for T to 6, which is computed by this, and the predecessor of T to S, right? Which is the source here, okay? And that's how we change the values for T, and also for Y, we also need to make the change, right? Because the old value for Y is infinity, which is greater than the S dot D plus the edge 7. All right, so that's the first pass. So after the first pass, you see, we can mark these edges to shaded color because we have these t dot pi equals s, the t dot pi equals the y dot pi equals s. Okay, so here's a typo. The y dot pi equals s. So this indicates the single source, the shortest path tree, right? These are the tree edges. Okay. All right, and all the values here are also updated. Okay, but that is just the one pass, right? We need to compute multiple passes, right? So in the second pass, we will basically do the same thing, right? And here, luckily, because the x, the t values, the t dot d's are now not infinity. So when we relax the the edge from t to x, the attributes for x will also be updated. Okay, the d's and the pi's will be updated for the x, but still for t to y, if we look at this case closely, the y dot d is 7, right, as indicated in the previous pass, but the t dot d is 6, right? So 6 plus 8 is actually greater than y, which means we don't need to update this one, right? Which means the pass from s to y here is a better pass than this way, right? So we will not update the estimate for y here. Okay, so we need to do that for all the passes in the middle, right? For some, we can change the values, but for the others, we can we simply make no changes depending on whether the if conditions are satisfied. Okay, so after the second pass, we can have such a shape of all the tree edges. Okay, but no, we should know that this is not the final results, because the algorithm tells that we need to run 4 passes. Okay, so after the third pass, all these values, the relaxation on all these edges will make no changes. And if we look at the value, if we look at the edge from x to t, okay, what is the original value for t dot d, which is 6, right? Which is 6. And the x dot d is 4. And then if we look at the edge from x to t, it's a negative edge, which means that if we go from s to y to x and then to t, which will result in a smaller pass, smaller weighted pass, which is 4 minus 2, which is 2, and it's smaller than 6. Okay, so that means we need to change the d of t to 2 and the pi attributes of t also to x. Okay, so that is a significant change in the graph. Okay, which means that we have to remove this shaded edge and add this one, right? Because here it makes a shorter path for t. Okay, and next there's a last pass, right? You may already notice that the values here is not accurate, right? We have to update this in the final pass. That's the values would become, the d for z will become 2 to negative 2. That makes sense because the weights for the edge between t and z is actually negative 4. So 2 plus negative 4 would be minus 2. Okay, so and to this point, we are pretty much done, and we have find the shortest path for all the vertices in the graph. So the shortest path from s to y is this one, right? To x, it should be this one. To t, it should be this one, and to z, it should be this one. Okay, and if we linked all the shaded edges with the vertices, it is a tree, single path shortest tree that we have found. Yeah, pretty similar to the way of how the BFS tree is found. Okay, so but now we need to examine whether there are negative weighted cycles in the tree, right? We need to run the lines from 5 to 8, right? We need to go through all the edges once, right, to see if there is a case that violates this if condition, right? And fortunately, in this case, we don't find any negative weighted cycles, so the Bellman-Ford will return, the algorithm will return true. Okay. All right, that's one complete example for the Bellman-Ford algorithm, which is a successful algorithm in terms of finding single source shortest path in the trees, and also examines whether there are negative weights in the tree. So it's actually a pretty broad application. It has less requirements on the inputs, right? We don't have to limit the inputs of the graph, right? We don't have to say that you should not contain negative weights, but it's okay to contain it because the Bellman-Ford will have a one last step to check whether there are negative weighted cycles in it, right? That's pretty much for the algorithm, but also the downside is also there, because if we analyze the running time for the algorithm, for the Bellman-Ford algorithm, we will soon find that it's actually not that cheap. Okay, so for example, the initialize so this part is fixed, right? We have to go through all the vertices. It will take a big O of V time. And for the relaxation parts, right? The outer, we have to consider two nested for loop, one nested for loop, which contains a outer for loop, right? The outer for loop iterates from 1 to V minus 1. So that is almost the big O of V, okay? And the inner for loop takes big O of E. So as we said before, it's almost V times E. So that'll take a big O of V times E in total, okay? And the relaxation actually is a constant basic operation, okay? And for the last for loop, it goes to the big O of E again, because it's another for loop that goes through all the edges, all right? So that taken into together, the Bellman-Ford algorithm actually runs in big O of V times E, okay? This quantity, if we look at it closely, we can actually think of it as something similar to a quadratic running time, because it's the product of two numbers, right? It's so different from the searching algorithms that we know so far, right? It's also different from the minimal spanning tree problem, right? Which is the logarithm of V, the logarithm of E times V, and so on, right? So we actually have so far the Bellman-Ford algorithm is the slowest algorithm. It runs in almost in this quadratic running time, right? So, well, that is also the trade-off, because we have no limits on the inputs, right? We said that the input edge can be negative numbers, and the algorithm has to be such a way that it has to have sufficient amount of passes so that the sufficient amount of relax operations are actually executed on the graph. All right, so that's it for the Bellman-Ford. I think I'm gonna skip the correctness of it, okay? In proving how the Bellman-Ford algorithm is correct, we actually utilizes the past relaxation properties of the relax procedures, right? That's something you can look at it yourself, right? And I think I'm also gonna skip this single source shortest path in DAG. And we know that the DAG, the directed acyclic graph, is a special type of graph that we talk about in the topological sort, right? So it actually requires that there's no cycles in it, right? So it's a good news for us, right? Because there's no cycles in it, and so we don't have to examine it, right? We don't have to examine whether there are cycles, and also it will make the single source shortest path more efficient. It will save our time from big O of V times E to big O of V plus E, which is basically a linear running time now, right? So I'm gonna skip it for now, and we can probably cover it sometime next week when we do the summarization, okay? So I think what's important today is that we covered the second type of shortest path problem, which is the Dijkstra problem. Yes, okay. So the Dijkstra algorithm, it has stronger requirements, okay? So comparatively speaking, compared to the Bellman-Ford algorithm, it actually requires that the input graph should have all the edge weights should all be non-negative, okay? There should be positive numbers or zero, okay? There shouldn't be negative weights. So that actually means that we don't need to worry about the negative cycles in it, right? Which also is a good news that it's probably a faster algorithm, okay? So yeah, for any edge in it, we must have a non-negative values, and this algorithm doesn't need to be, is not like a Bellman-Ford. It doesn't use two nested for loops to relax all the edges for sufficient amount of time, but instead it actually maintains a set of vertices, okay? And it will repeatedly select vertex from V minus S, okay? And it will add that vertex U to the S and then relax all the edges, leaving U, okay? So it's kind of similar to the so in terms of this style, right? It starts from nothing, right? That set of vertices should be empty, and then it will progressively select vertices, right, in the remaining set of vertices, and that is pretty similar to the Prim's algorithm, right? In the Prim's algorithm, we also select vertices and then check whether that's and then we will apply some operations on the vertices selected. Okay, so in this case, we would use this similar style. Okay, so the problem is, how do we select the vertex that has the minimum shortest path estimates, right? And also the answer is almost there, because in the Prim's algorithm, we use the minimum priority queue, right? And in this case, we will also use the minimum priority queue. And the key for that minimum priority queue will be this distance estimate. Okay, we will put all the vertices in the queue, and then we will extract one vertex at a time, and that will be the one that has the shortest, that has the minimum shortest path estimates. Okay, so yeah, we will again need to use a minimum priority queue for all the vertices. So the Dijkstra algorithm basically looks like this. First, it's very similar. We need to initialize all the D's and the Pi's, right? And then we will need to initialize a empty sets, okay? So these empty sets will be the one that contains the final the final shortest path tree, okay? And then we will put all the vertices in the minimum priority queue in line 3 here. Next, it comes with the for loop. This for loop will never end. No, it will not end until the queue is empty, okay? So within each body of the for loop, right, we will extract the elements, the minimum elements from the queue, which has the smallest D property, right? And that one will be merged, will be union to the sets, okay? And what comes next is the critical stage, right? It is where the relax occurs. it will examine the each vertex within the adjacency list for that vertex which is just extracted, okay? Which means we have to relax each edge, right? Leaving U, right? And then we will run a relax on that edge, okay? So if we look at the algorithm, the while loop actually iterates exactly V times, right? Because we put all the V's in the queue, right? So we will basically let the while loop iterate over V times, right? Because it will never insert vertices back to the queue, right? And each vertex is extracted from queue exactly once, right? So it's kind of a greedy strategy, right? It's kind of similar to the Prim's algorithm that we select the lightest vertex, right? So let's look at the example here. It's a graph that looks like this, right? And the difference from the Bellman-Ford algorithm is that we don't have a negative numbers here. We should not have negative numbers here. And the minimum priority queue after initialization looks like this, right? We have all the D's initialized to infinity except for the source vertex, right? And the set S is initialized to empty, right? So the S, the lowercase s will be the one first extracted because it is the source, okay? And we need to relax the edges that leave the source, okay? So in this case, we have to relax the edge from S to T and the edge from S to Y, okay? After relaxing them, the D values for the T and for the Y needs to be updated, right? Because that's what the relax procedure does, right? It will update the D values depending on the conditions. All right, so that is the first, after the first vertex extracted. And so that'll change the keys within the minimal priority queue. So the Y now has the smallest distances. Okay, so now the Y will be the one next being extracted. Okay, so after Y is extracted, okay, we have to insert Y to the S, and then we have to relax 3 edges. Okay, because Y has 3 edges. The one from S to T, from Y to T, from Y to X, and from Y to Z, right? So it's particularly interesting to look at the value of T, right? Because the old value for T is 10. But if you go by Y, the D of Y plus 3, it will be a smaller number, 8. So it will change the pi attribute of T to Y. So the T is now edges. So the edges from Y to T is now a tree edge. Okay. So now we have 3 elements left in the minimal priority queue, and then the next one being extracted would be Z. Okay. After Z is extracted, there will be 1 edge being relaxed, which is the edge from Z to X, right? Which also updates the value for X because the values of 7 plus 6 is 13, which is smaller than the old value of 14. Okay, and then 2 edges left, 2 vertices left. We still need to extract the mean values, extract the mean elements, which is T, and then we will extract, we will need to relax the edges, right, from T to Y and the T to X, okay, which will further change the D of X to an even smaller number, right, which is 8 plus 1, which is smaller than 13, okay, and the X will be the one that's left, okay. And the oops, I think it should be 9, not 14, right? Right, it should be 4, it should be 9, not 14. So that is the results after the all the vertices in the minimal priority queue is extracted, and the results of this Dijkstra's algorithm on this graph looks like this. Okay, so we are done with the algorithm. So it's actually, you know, less steps, fewer steps than the Bellman-Ford algorithm, right? If you you can do the computation, because after each vertex is extracted, we will only examine the edges that's leaving that vertex, right? We will not relax the same edge for multiple times. So it's actually a more efficient algorithm. Only if we only consider the number of how many times over each edge is relaxed. But I think it's important to notice that why Dijkstra's algorithm is correct, and it actually has something related to the requirements. Remember, we require that the Dijkstra should be the algorithm should run on the graph with no negative weights. Okay, with non-negative weights. So all the edges should be positive or zero numbers. Okay. So this correctness of Dijkstra's algorithm, in order to prove it, we just need to show that the estimated value u dot d is already the theoretical minimum points. Okay, at a time that u is added to S. Okay, after each time a u is extracted from the minimum priority queue, we have to show that at that time, the minimal, the d values is already the theoretical minimum theoretical minimal value, so that it will hold or at all times after, according to the convergence theory of the relaxation properties. Okay, so actually these prove. Let's go through this quickly. Okay, so in order to prove it, we will use the contradiction method. So we will let u be the first vertex. Okay, we let u be the first vertex that doesn't satisfy this equality. Okay, doesn't satisfy this equation, that which means the u dot d doesn't equal the delta when it is added to S. Okay, so and we assume that the u is the first one, that we have such a violation. Okay, then we must there must be some shortest path from S to U. Okay, so let's say S looks like this. S is a subset of all the vertices in a graph, right? And we assume that there must be some shortest path from S to U, right? Which is a shortest path that we indicate by P. And then we can decompose this path P into two segments, which is P1 and P2, okay? And which is separated by the two imaginary vertices in the graph, okay? And we let Y be the first vertex along P, such that the Y is outside S, okay? And let X be the Y's predecessor, which means X is the immediate predecessor of Y. Okay, so we basically decompose the shortest path to two segments, actually three. First one is a path, and then one edge, and the second path. Okay, so that's some decomposition, and let's see what contradiction we can get. Okay, so because we let U be the first vertex that violates these requirements, that violates the assumption, the UD doesn't equal the delta value. So we must have that we assume that U is the first one. So everything before U should have this equation valid, right? Because X is added to S before U. So this quantity, X dot D, must equal delta of S to X, right? Because that's our assumption. Okay, so when X is added, the edge from X to Y is relaxed, right? So by the convergence property, okay, the convergence says that we must also have the, once X has reached the theoretical minimum points, and then we relax the edge from S to Y, then we must have the Y dot D also reach the the theoretical minimum points. Okay, so that's by the convergence property. So now we can actually observe a contradiction, right? Because Y appears before U on the shortest path, and all the edges are non-negative. Okay, so the theoretical minimum points, minimum value for U must be greater than Y, right? Because U is at a later stage, right? When we go from Y to U, there is a path P2, right? So because all the weights are non-negative, so the delta values for U must be greater than the delta value for Y, right? Because that's determined by the property of the graph. All the edges are positive numbers. So we must have the Y dot D should be smaller, less than or equal to U dot D. Okay, right? But because both the Y and U, they are outside the S when we choose U, right? So there must be U dot D be smaller than Y dot D, because U is the first one we pick, right? U is the first one we pick. No, U is picked before Y, right? Because it is the first one that violates this property, right? So U is picked before Y, and everything outside S is managed in the minimum priority queue. So by the property of a minimum priority queue, we must have the D values of U must be smaller than D values of U, D values of Y. So here it's just in order to have these two inequalities to be both valid, we must have the D values of Y must equal the D values of U, right? So, but that apparently violates our assumption, because we assume that the D values doesn't equal this delta, which further means that our assumption is incorrect. Okay, we must conclude that when the vertex U is picked from the minimal priority queue, the delta of it must already reach the theoretical minimum points. Okay, so that basically proves the correctness of Dijkstra's algorithm. And now we also see that why it is important that Dijkstra's algorithm should apply to non-negative edges. Okay, so because if there are negative weights in the path, then we are not sure that whether along the P2 there's negative numbers. So it's possible that it's possible that the delta of U can be smaller than the delta of Y, because there could be some negative numbers along the path here, right? So if that is the case, then we cannot make sure that Dijkstra's algorithm is correct. So we have to stick to the requirements that everything should be non-negative. All the edges should be non-negative. So last, let's quickly analyze the running time of Dijkstra's algorithm. And it's again about minimal priority queues. So we have to be careful about the implicit operations. So there's insert, which is implicit in 3, right? There's an extract minimal in line 5, And because we update the values, after we have updated the values in the minimal priority queue, we have to run the decrease key, for example, or if it's managed by a minimal heap, then we have to call minimal heapify, right? In line 8. So, and then because each vertex is added to S once, and each of its adjacent edge is also examined exactly once. So the for loop actually iterates for E times in total. It only examines all the edges once. And the decrease key is called the E times. So the running time depends on how efficient our implementation for the minimal priority queue. So that is an old problem now. So if we assume that if it's a minimal heap, then each heap operation takes the logarithm of V times. So taking that into consideration, we have to say that the total running time is proportionate to this value, which is big O of V plus E times logarithm V. Or we can say that it's big O of E times logarithm of V. Okay, so now it's a significant improvement as we compared it to the Bellman-Ford algorithm, which is big O of E times V. Okay, as we introduce this logarithm term. All right. Yeah, I think that's so much for the Dijkstra's algorithm, and I think we have covered all the single source shortest path algorithms for this chapter, which is our last chapter for the advanced graph algorithms. And we didn't cover the DAG, right, the directed acyclic example. I think we can do that next Tuesday to cover that a couple of slides, so that we can talk about, so the next Tuesday we will cover our last lecture about in this whole course, and then we can talk about the final exams. Okay, the last slide is a comparison of the Dijkstra's algorithm with the BFS and the Prim's algorithm. So you can, I would encourage you to go through these slides more carefully. Okay, so we are limited by our time here today, and I will release the assignments, our last assignments for the advanced graph algorithms, and also there will be a quiz question today. Okay. All right, thank you guys. I will see you next Tuesday.